Okay, we're recording. Test 2 is going to take place during the first full week of April. So it'll be posted on Wednesday, April 7th, and due on Friday, April 9th. So what I will be doing is over the weekend, working on composing a test and a practice test like last time. So I can try to get that posted by a week from today, by Monday, the 29th. So you'll have some time to look at it before class on April 5th, Monday, April 5th, which will be a review. Um, but just make sure that when you do take the real test that you pay attention to differences in the problem statement between the practice and the real one, so we don't have a preventable loss of points like we did last time. Okay, so keep an eye out for that. I'll bring it up again next Monday to indicate that it's been posted. Okay, now getting into lesson 24. Okay. Right. Now, last time we took a brief digression from a wave equation on an infinite domain to talk about finite vibrating string, solving a wave equation on a bounded interval where you had bounded conditions at both ends, and for that, use separation of variables. But we're going to go back to problems involving a wave equation on an infinite domain on the entire space to talk about 2 and 3D problems. So far, this entire chapter on the wave equation, we have only been considering a wave equation in one space dimension. So now we're going to look at 2D and 3D, but with a simplification of not having to concern ourselves with boundary conditions, but only how the initial data ends up dictating the behavior of the solution over time. Now, you might think that we would start by talking about the wave equation in 2D first, but it turns out to be easier to start with the 3D problem, and then we will specialize that to the case of 2 dimensions using an approach called the method of descent. Okay. So it turns out there is a surprisingly simple formula for the wave equation in 3 dimensions, or at least it's a way to express it simply. But arriving at it is not so simple. But I'll take you through it. So the problem we're going to be looking at is so here's a wave equation in 3 dimensions. Now, so instead of a customary uxx you're used to from a one-dimensional case, udt is equal to a constant c squared times the Laplacian of u, which also can be written in this way. Delta u, here it's written as this gradient symbol squared applied to u. And really what that means is it's not literally squaring, it's the divergence of the gradient of u. But this is a formula for it. So it's the sum of all the second partial derivatives with respect to the same variable twice. So in one dimension, you're accustomed to uxx, so we just add on uyy and uzz. Yeah. And this is on all of 3-dimensional space. and we have our two initial conditions. So in this problem, u is set to be 0 initially, but we do have an initial velocity given by some function psi of xyz. So we're going to solve this problem first, and then consider the opposite case where this part of the initial data is non-zero, and then we can just add the two together to solve a most general case of both being non-zero. So the way we can solve this problem most easily, since we're considering a problem on all of R3, is use a Fourier transform. So a Fourier transform, what it looks like in 3 dimensions, is this. So this is a natural generalization of the Fourier transform in one space dimension. Because before we'd have e to the minus I omega x. So now we have omega 1, omega 2, omega 3, 3 Fourier variables corresponding to x, y, and z. So you can also think of this as a dot product of the vector omega 1, omega 2, omega 3 with x, y, z. And we have a scaling factor. It's 2 pi to the dimension over 2. So whatever number of space dimensions it is, it's a 2 pi to that over 2. So if we take the Fourier transform of both sides of a PDE, then on the left side we're just going to get the Fourier transform of UTT. So it's UTT hat. It's the second derivative with respect to time of U hat. And then on the right side we'll have C squared, and then taking a Fourier transform of a second derivative with respect to x causes multiplying by the corresponding omega squared. So here before we had uxx plus uyy plus uzz, so that's what leads to minus, and then we have omega 1 squared plus omega 2 squared plus omega 3 squared coming from these differentiations. All of that times u hat. So this PDE, when Fourier transformed in free space dimensions, gives us this ODE for t. So now we just have to solve this ODE with these initial conditions. So u is 0, therefore u hat is 0. And then we take a Fourier transform of this initial condition, and that gives us the initial condition for our ODE, where we have the Fourier transform of psi, whatever psi is. Okay. So this is ODE in t with these 3 parameters, omega 1, omega 2, omega 3. So this ODE is no more difficult to solve than the ODEs we've gotten from other problems where we've taken a Fourier transform. The fact that this came from a 3-dimensional PDE doesn't lead to a more difficult ODE. The solution would just be okay. The initial data that we had. Okay. And then we have sine of c times the magnitude of omega, which is the magnitude of a vector from 3-dimensional space. It's a square root of sum of squares that you would know from calculus, times t divided by c times that magnitude. So this solution can be arrived at using the usual technique for a for solving a second order linear ODE of constant coefficients. So to see where the solution comes from a little more clearly, first I want to simplify how it's written using a notation I've introduced since then. So so it'd be minus c squared times the magnitude of the vector omega squared. And actually, I'm going to just write that as that whole thing being squared. So what you would take from your first ODE class is that the general solution will be equal to some constant, which I'll call C1, times cosine of whatever is squared here times t plus another constant times the sine of that and to get the values of C2, C1 and C2, it comes from initial conditions. For example, if I plug in t equals 0 here, this would go away. This is 1. I would only have C1. But it's supposed to be 0. So it turns out there will be no cosine term. If I take a derivative of this with respect to time, I would get C2 cosine of this times C omega. And that is supposed to equal this. So that's what leads to the division by C magnitude of omega here, and having only this sine term. So what we have here is the Fourier transform of a solution of our wave equation. So we need to take the inverse Fourier transform of this to get to the solution of our original problem, and that would be u, no hat, u of x, y, z, t. So, taking an inverse Fourier transform, even for an arbitrary given function psi here, can be quite a chore. Okay. All right, so I'm taking inverse Fourier transform. First, I'm only going to focus on the part of this that excludes the psi. So sine c omega t over c omega, where I'm being lazy here and saying omega, when I really mean magnitude of omega. So if I take a Fourier inverse transform of this part, and I know how to take the inverse transform of this because it would just be psi of x, y, z, I can use convolution to put those two inverse transforms together and get the overall solution formula. So how do we take the inverse Fourier transform of just this part? So here's a formula for 3D inverse Fourier transform, which is exactly the same as the 3D Fourier transform, except you don't have a minus when it's the inverse. And we're integrating over all three-dimensional space. So you think of this as d omega 1, d omega 2, d omega 3. Okay. So what can we do with this? I'm going to express this in spherical coordinates, but a rather unusual sort of spherical coordinates. So I need to explain that before I continue. So the idea is in spherical coordinates, normally you have the North Pole of a positive, going up a positive z-axis, and you have the angle of inclination phi that corresponds to the North Pole. But now I'm going to have a North Pole pointing in the direction of whatever vector x, y, z that I have, because this whole expression is a function. Once I evaluate the integral, this whole integral is a function of x, y, z. So you can, but I'm integrating with respect to omega 1, omega 2, omega 3. So you can think of x, y, z as being parameters. So for whatever x, y, z I have, I'm going to use basically, you think of it as a tilted or rotated spherical coordinates where the North Pole is pointing towards wherever x, y, z is. And the reason why I do that, it simplifies things tremendously in the integral, because in these tilted and rotated spherical coordinates, in the direction of x, y, z, I have it basically corresponds to the point 0, 0, r, where r is the magnitude. So I'm working in this coordinate system that's oriented around the direction of x, y, z. So what that effectively means is, only in this coordinate system, only the z coordinate is non-zero. That would be r. Okay. Now, in spherical coordinates, this expression, actually, I'm going to just list the spherical coordinates. So omega 1 in spherical coordinates would be rho, which is magnitude, cosine theta, sine phi, and then omega 2 would be rho sine theta, sine phi, and then omega 3 would be equal to rho cosine phi. And rho is the square root of sum of squares of all the omegas. Okay. So because we're working in this modified spherical coordinates where position position vector x, y, z is the North Pole, this dot product is dot product of omega 1, omega 2, omega 3 with 0, 0, r. So it's just omega 3 times r. And omega 3 in spherical coordinates is this. So that's how I get this right here. So the r comes from the z coordinate of x, y, z. This comes from the z coordinate of omega 1, omega 2, omega 3. Now rho is also the same as the magnitude of a vector omega. So that's how this becomes rho, above and below. And then don't forget, when you're doing an integral in spherical coordinates, you have to include this factor. This is the Jacobian of a coordinate change from Cartesian to spherical coordinates. And I will also offer an apology to any physics majors we have here, because I'm using the mathematicians' conventions for spherical coordinates, which is different than what physicists used. So sorry for any confusion that causes. Okay. All right. Now, to evaluate this integral as best we can, notice that the entire integrand, that's everything I've highlighted here, has no dependence on theta whatsoever. So the integral with respect to theta, I can just go ahead and do that. That would give me a factor of that would give me a factor of 2 pi. Okay. So that's how this 2 pi to the 3/2, the denominator here becomes just 2 pi to the 1/2 in the next step. So the integration with respect to theta has already been carried out. Also, this integrand can be expressed as a function of only rho times a function of phi. So I can separate those. So this integral can be evaluated with respect to phi, which would give me a function of rho, and then that can be evaluated. Now, to evaluate this integral, I perform a u substitution. U is equal to cosine of phi. So that gives me the u right here. Because then du is equal to minus sine phi d phi, which would absorb all of this. And then if I plug in the limits 0 and pi in for phi, my new limits become minus 1 to 1. So now I can actually go ahead and evaluate this inner integral. So I go ahead and do that, and that's what gives me this part right here. So now I'm down to just a single integral with respect to rho. But I can actually keep in mind that this difference of complex exponentials here, this is the same as 2i times the sine of r times rho. So that's what I fill in here. And then I have a bunch of constant factors to sort out. So once that's all taken care of, this is what I'm left with. The r is a constant. It doesn't depend on omega 1, 2, or 3. So I can just pull that out. Here I have a product of signs. You can use a trig identity, a product to sum formula, to express this product of signs as a difference of cosines. And if you consult a table of Fourier cosine transforms, then what you would end up with is this, the delta function, a Dirac delta function evaluated at r minus ct. The Dirac delta function is not technically a function. It's called a distribution. You can think of it as being 0 when its argument is not 0. But really, the idea is if you integrate it over the entire space, like from 0 to infinity, what you would get is 1. So it's a way of selecting a particular point at which it's not 0. So this is what we get for our inverse Fourier transform of this. So any questions about what happened here? That was kind of a mess. Yes? Sorry, I couldn't hear. Someone have a question? I thought I heard somebody. Okay. All right. So now that we have, that's only an inverse transform of part of it. We need to put the whole solution together. So our solution u of x, y, z, t is the convolution of psi with the inverse transform that we got above. I just want to check something here against what's in the textbook. Lesson 24. Okay. All right. Oh, okay. I need to introduce some notation here. Here I have this r prime. R prime is a so it's a distance between the point x, y, z, which is what I'm evaluating my solution at, and x prime, y prime, z prime, which is from the integral. So, so to try to evaluate this integral, I can't evaluate the entire thing because I have this unknown function psi. But what I can do is once again work with let's see, spherical coordinates. But in this case, all right. Okay. All right, I need to add some intermediate steps here to make clear what's going on. All right, so because really what we have is, if I'm going to express this properly in spherical coordinates, what we have here is put in spherical coordinates and then an extra step taken, which is not shown. So I need to show that step. So I'll have the same scaling factor out front. Whoops. Okay. And in spherical coordinates, I'm going to have integral from 0 to 2 pi, 0 to pi, and then we're integrating over all of three-dimensional space. So I also have integral from 0 to infinity. And when I express this in spherical coordinates, so psi is evaluated at x prime, y prime, z prime, but in spherical coordinates, that would be with using x, y, z as the origin to simplify matters. So I'd have x plus rho cosine theta sine phi, and then I have y plus rho sine theta sine phi, and then z plus rho cosine phi, and then I have this expression here from my other inverse transform. Okay, and then rho squared sine phi d rho d phi d theta, and it's running off the page. Okay, I'm gonna have to do it like this. Okay, just to fit it. So here's my function psi expressed in spherical coordinates with x, y, z as the origin. And then I have a typo here, d rho. Okay. And then I have this carried down here. And here we have change of variable from Cartesian to spherical coordinates like before. But then I can actually evaluate the part of it as being integrated with respect to rho right away, because what we have here, this r prime, that's rho. It has the same meaning. So this would be rho minus ct, and then similar down here. Okay. But then once I evaluate that, this part, this is how a Dirac delta function works. I'm integrating this from 0 to infinity, but the delta function is going to give 0 everywhere except at rho is equal to ct. So so the evaluation of this innermost integral with respect to rho going from 0 to infinity is going to have the effect of this entire integrand having rho replaced throughout with ct. And that's what leads to what we see down here. In the arguments to psi, rho is replaced with ct. This part effectively becomes 1. So that's how a Dirac delta function or distribution works. And then I still have a pi over square root of 2 pi here. And then you have c down here, and then this simplifies to rho, but rho is equal to ct. Okay. And all right. And so we have here, this rho squared became ct squared. Here I have c squared t, which I just pulled out of the integral. And then I have these constant factors that I pull out too. And after cleaning up all the constant factors, this is what's left. So now all I have left is this, the integrated with respect to phi and theta. But what I can do is simplify how this is expressed. This is, if I were to multiply and divide by t, then I would have t times all this, which is everything else we have here. And that's the average value of psi over a sphere of center x, y, z, and radius ct. So the overall solution to the original wave equation problem is just this. It's t times the average of your initial velocity over this sphere. Any questions about how this problem was solved? Now in this problem, u was 0, du dt was not 0. What if we go the other way? All right, so now we have u equal to phi at time 0, and du dt is 0. So to that, we return to the problem we had before, where, so now we're solving the wave equation for v. V is 0 at time 0. dv dt is equal to this initial data. This is a problem we solved at first, so we have a solution formula for that. So we have that for v. But how does v relate to the solution u of this problem? It turns out there actually is a simple relationship. Because if I look at dv dt and take its second derivative with respect to time, then that would turn out to be equal to c squared times the Laplacian of dv dt. So in other words, v satisfies the wave equation. dv dt also satisfies the wave equation. What initial conditions does it satisfy? Well, dv dt at 0 is equal to phi. And then the time derivative of dv dt would be equal to, at time 0, would be equal to the average value of phi over this sphere, centered at xyz radius ct. But we're taking a time derivative of this, evaluate at t equals 0, and that's going to give us 0. So what that means is u is just dv dt. So now we have a solution of this problem too. So it's just the time derivative of a solution of the problem where we swap these two initial conditions. So now we can put the two initial data together. For most general case, so if we have whatever given initial data, okay, I should put xyz here. Okay. So u is equal to phi, du dt is equal to psi at time 0. Then I can put two solution formulas together that is equal to time derivative of t times the average value of phi plus t times the average value of psi, where the averages are taken over a sphere of center xyz and radius ct. Now, this formula that we have here, this is called Kirchhoff's formula, also known as Poisson's formula, but that's really mainly applies to the two-dimensional version, which I'll show in a bit. So this is a solution to the free space wave equation. So problem solved over the entire three-dimensional space with whatever initial conditions. So here's how that can be interpreted. So suppose you have initial data 0, except within a small sphere. So the initial data is concentrated in space. So what happens is, if you're evaluating the solution of a wave equation at some other point, x naught, y naught, z naught, that is outside the sphere, like far away, you're taking the average value of your initial data over a sphere that's centered at this point and has radius ct. So if you're interested in how a solution behaves at this point over time, you're averaging the initial data over a sphere that is growing and growing. So if this point is far away from the portion of free space where the initial data is non-zero, your solution is going to be 0. And that will not change until time is large enough so that the sphere centered at this point is large enough to intersect with where the initial data is non-zero. So only then are you going to see something non-zero in your solution. And once that time is large enough for that radius to be large enough, then immediately you're going to have something non-zero. And so that's what's called a sharp leading edge in a solution. So when you start to see something non-zero, and then the sphere is going to continue growing. So at some point, the sphere will grow so large that once again it'll avoid the portion of free space where the initial data is non-zero. So because the thing is, we're evaluating this integral over the sphere. So if I take a look at this integral, this average that we're taking, it's integral with respect to phi and theta, but not with respect to distance from the center. It's over or just the sphere, not the ball. It's not covering the interior, only the boundary of this ball, the sphere. So what that means is, once the radius is large enough so that the ball So I should say, reword this. The ball centered at this point contains the sphere. I should say ball here also, just to. Sorry, but terminology was not consistent. Okay. Okay. All right. So then this sphere sitting at this point of radius CT is no longer intersecting where the initial data is non-zero. So the solution ends up being 0 again. And it'll stay 0 for all time after that. So we have a sharp trailing edge. So if you're just monitoring a solution at this one point, x naught, y naught, z naught, it'll be 0, 0, 0 for a while, then suddenly becomes non-zero for a period of time, and then it'll go back to 0 again. So when you have this initial data, the non-zero portion concentrated within a small region, that's how the solution of a wave equation in three-dimensional space behaves. And the fact that it behaves this way is called Huygens principle. And what's odd about it, and I just realized I accidentally punned, is it holds in odd number dimensions, except dimension 1. So 3, 5, 7, and all odd number dimensions after that. But otherwise, no. And we already see it doesn't hold in one space dimension because of D'Alembert's solution formula. It has an integral of the initial velocity from x minus ct to x plus ct. So if this g of x is non-zero only within a small interval, you're integrating over a larger and larger interval. So as once time grows large enough, it will always contain this portion where g is non-zero. So there will always be a non-zero contribution of a solution from that point on. So questions about behavior of a 3D solution. Oh, wow. Time is passing quickly. Still talking about 2D. So what we could do is take our 3D solution formula and express it in a form that corresponds to 2 dimensions. Basically, we're going to flatten it for a case where initial data depends only on x and y. So now we're talking about, instead of spherical waves, it's like cylindrical waves. So by change of coordinates, we can obtain a formula for the 2D case. So here's our two-dimensional problem. And again, we have the solution being 0 at time 0, and then we have some initial velocity. So using a formula from a 3D case, this is what we have. So I'm just repeating a formula from before. That's t times the average over this sphere of center x, y, z, and radius ct. But now I want to have an integral over a two-dimensional entity. So instead of working with a sphere of radius ct, I want to integral over a disk of radius ct. And so to convert the integral over a sphere to an integral over a disk, we perform what's called the method of descent. But it really amounts to a change of variable. Okay. So in spherical coordinates, we have a variables phi and theta. So we're going to change the variable phi to the polar coordinate variable r. Now, to get a hold of the angle phi that we're going to change, we use this relationship that the z coordinate from spherical coordinates is equal to the radius times cosine of phi. So I just rewrite that relationship to give this. But using right triangle trigonometry, the radius is equal to square root of x squared plus y squared plus z squared. And r is equal to square root of x squared plus y squared. So I can express z this way. Because z is any point on the sphere of this radius. And we just need to subtract off the x and y part. So now I have a relationship between the spherical angle phi and the polar coordinate variable r, where everything else in here is a constant. So now I can take derivatives of both sides of this to get d phi, which I have in here I need to replace with something involving dr. So I take the derivative of inverse cosine, and then by chain rule, I get all this mess, which thankfully simplifies quite a bit. And in fact, I end up just with this. So now I also have this relationship that r is equal to ct sine phi. This actually follows from right triangle trigonometry. And the fact that psi is the angle of inclination from the north pole of your sphere. So here's our solution formula. It's t times this average over a sphere. And this is what we have from the 3D case. I've removed the z part because psi is a function of only x and y, not z. So at this point, it's still in spherical coordinates. Then I use my change of variable. So d phi gets changed to this expression here. So that leads to this radical here, and then we have dr. And then here I have sine phi, but that's replaced with r over ct. So now I simplify as much as I can. Also for the limits of the integral, since this is my change of variable, phi is going from 0 to pi. But that's the same as r going from 0 to ct. So that explains the change in limits that we see here. Also, we get an extra factor of 2 that comes from the fact that we're descending for both the top and bottom of the sphere, and that descending from positive z or negative z still has the same value of phi. So that's where that this factor of 2 comes from. So by the time we simplify everything we can, then this is what we get. Okay. So this is Kirchhoff's formula scaled down to 2 dimensions. Using the same approach as in 3D, to account for the 2 pieces of initial data. So what I have here is u of xt. Oh, that should be u of xyt because we're in 2 dimensions. Okay. So that's equal to this formula applied to psi, the time derivative. That should be 0. And then we have the time derivative of a same averaging formula applied to this piece of initial data, phi. Now, a contrast to the 3D case. In the 3D case, we were integrating over a sphere, only the boundary, not the interior. Here, we're integrating over the entirety of a disk of the center xy and radius ct. The interior is included in this integral. So we're not going to have that sharp leading edge or sharp trailing edge. If you have a point that's far away from where the initial data is non-zero, initially, yes, the solution will be zero. But, so it's actually, you do get a sharp leading edge. You do not get a sharp trailing edge because once you have that non-zero-ness, if you will, in your solution, then generally it will remain there for all time past that point. So this is the kind of behavior that you can expect in a even number of dimensions. Okay. Okay, so we have some time. Do we have any questions about this or about any ongoing homework? Okay. Well, the last homework I graded, homework 5, that went quite well for everybody. And I see people, not too many people have turned in homework 6 yet, but once we have critical mass there, then I will go through those also. Okay. So, all right. Looks like my brain frying work here is done. So I will end recording at this point. Anyone is welcome to stick around with questions if they have them.